Section 6.1 is the set of rational numbers, and we're going to take a look, this is sort of our introduction to this section, of what is meant by rational numbers, some vocabulary to start with. We're going to just define what most people think of. There's a couple things, but one of the things they'll think of with rational numbers is the word fraction. So a fraction is really any number of the form a over b, as long as the denominator is not 0. If the denominator is 0, we would call that undefined. The numerator is the value on top, and of course the denominator is the value on the bottom. Now rational numbers are actually a number of the form a over b, or it can be written in the form a over b. But specifically, a and b have this extra condition. What's that condition say? Yeah, a and b are integers. And maybe they don't actually look like integers to start with. Like for instance, maybe something starts out looking like 4.1 over 6. Well, I mean, 4.1 is not an integer. Integers are like whole numbers, positives and negatives. But we can change the view of that fraction, and we'll talk more about this later, but we can change that, for instance, by multiplying by 10 on top and bottom. So it becomes 41 over 60. And 41 and 60 are integers. So it doesn't necessarily have to be something where it's already written with integers, but it has the ability to be written as integers is the key idea. Okay, so those are rational numbers. So in particular, we're going to be looking at fractions in this chapter. I know, it's the one you wanted to start with, right? Mm-hmm. Fractions. They're fantastic. They're so wonderful. You guys are going to love them. At least I hope you'll tolerate them. So we're going to look at this chapter of fractions, and in particular fractions where we have numerators and denominators or integers. So we're not looking at other types of fractions. You've probably seen some other types of fractions if you've taken geometry or trigonometry, things with pi involved, like pi over 6 or something like that. It's not rational because pi doesn't have the ability to be turned into an integer just by multiplying by something. So there are definitely numbers that don't fit into the category we're looking at, but we are specifically focusing on those integer ones today. There are 4 uses of rational numbers. The first use of rational numbers is solution. So what do I mean by that? Well, it means it has the ability to be used to solve equations. Like 2x equals 1. If we only have integers, then we have numbers like -1, 0, 1, 2, 3, so forth. And if those are the only numbers that quote-unquote exist, or that we have that we can use, none of those numbers will solve this equation. If I put in 0, 2 times 0 is 0. If I put in 1, 2 times 1 is 2. And I just skipped right over what this is supposed to equal, which is 1. So I don't have the ability to solve this problem if I don't have rational numbers. So that's one of the uses of rational numbers. Another use is partition. And so a partition is something like this. If we say 1/4, 1 out of 4, right, like this, also known as 25%. We're not doing percents in here, but 1/4 of my paycheck goes to gas. Pays for the gas in my car. It is a partition or a portion of something else. Okay? So that's one use of fractions, is to use it for a partition, a portion of something else. Another one is ratio. So an example of ratio might look something like this. The teacher student ratio is 1 to 8. It can also be written like this, 1 over 8, like that. Or it can be written like this, 1:8. I'll define all that later, but those are 3 ways that we could write when we're really talking about it being a ratio. And the fourth one is probability. So an example of that would look something like this. When you roll a die, you have a 1 out of 6 probability of rolling a 4. So it's the chance or the likelihood of something. That's what probability represents. And we will do more with probability in chapter 9, I think it is. So we're going to use rational numbers for all of these concepts. All right, so what we're going to start with is we're going to start with some pictures that will often be used in curriculum that you're likely to see. My daughter she was in Shawnee Public Schools to start with, and she started encountering fractions, I think it was in 3rd grade. And it isn't complicated stuff. She started encountering pictures like these. Okay? So you are likely to see some pictures like these in younger grades than you might have thought you would. And so what we're doing is we're looking at these and we're going to answer the question to write a fraction that represents the shaded portion. So first of all, we're going to answer the first question, and then we're going to think about what kids might say when they look at this question. So what is the right answer for this question on part A? It is 1/6. What do you think an answer might be if you were first teaching this to a young child? 1/4. Why would they do that? 4 boxes, and one of them shaded in, right? So what would be the reasoning that would be wrong about that? What would they be doing that would be wrong reasoning for that?
All the boxes are the same size.
Right. In order to do this, all the boxes need to be the same size. Now on this one, that's not too difficult to fix. We can just drop in a couple of lines and you can make equal size boxes, or at least approximately equal, right? Just draw in a couple extra lines here. And we can say, oh, look, but see, there's 6 boxes, and one of them shaded in, because those boxes are all the same size. Now, part B is very similar, but it's even more misleading than part A, probably. The correct answer for part B is what? It is 1/4. But again, many kids, would probably say the answer is 1/5. And it's even more reasonable to do that because this is very misleading. The first one looked like, oh, it was just missing a couple of lines. But on this one, like, they've actually drawn in 5 boxes, and they really don't look all that different in size. Are they different in size? Well, of course they are. But they don't look that different in size compared to the first diagram. And so again, what we would have to do is we'd have to repartition our image so that students could clearly see where, let me use the pink, where the boxes that are equal would actually be and how many of them there would actually be. So you would be redrawing something like this to say, no, see, if we actually had all equal boxes that are the same size as the one that's shaded in, there's really only 4 boxes here. How about C? 2/7. Very good. The tendency on this particular diagram is just when you're counting the images around in the pie is to lose track of your slices of pie, depending on how many pie slices you have. For instance, you might have a kid looking at this one and immediately say it's 2 out of 8, because normally when we split up a pie, 8 would be a reasonable thing to split it into. 7 is a little awkward. So it's just being careful to count the slices of pie. And one of the things you can do when you're counting is you can just mark that you've counted them, in some fashion or another to make sure that you've got all of them there, that you've done your counting right. D is a very different image. Let's answer the question first, then I'll talk about why this image is so very different. What's the answer for this one? 7 out of 12. So let me ask you guys, what is it about D that's different, really different than A, B, and C?
They're not connected.
They're not connected. Very good. What we would actually sort of describe this as is that these like A, B, and C, is that they're sort of like one whole diagram split into pieces, right? But D does not have the same feel as that. There's sort of all these disjointed or disconnected images, and a portion of them have some sort of a relationship that the other portion don't. In this case, they're shaded versus not shaded. And so it's a very different kind of an image. And very honestly, kids can look at A, B, and C and see why fractions would make sense, but look at D and be like, why is there a fraction? Because there isn't a whole to compare it to. So it's kind of a different concern on that one. Some historical aspects about fractions that you may or may not know. Egyptians actually used fractions, and be glad you're not an Egyptian back in the day, because this looks really hard to me. They used fractions that all had numerators of the number 1. So if they wanted to represent the number like 7 over 12 that we just used, they wouldn't write 7 over 12. The way it would have been represented is 1/4 plus 1/3. That feels very awkward to me. But they didn't have the notation that had anything but numerators of the value 1. So kind of an interesting information. Greeks. The Greeks adopted fractions with denominators of 60 from the Babylonians. This is still presently used in the measurement of angles. There's another thing we use with 60s. Do you know what it is? Clocks. Which makes sense because it's related to the idea of an angle, at least in some degree. To some degree. Did you get it? To some degree? Yeah, okay. Good. Good. You guys are paying attention. All right, the last one, the Hindus. The Hindus actually developed the modern bar between our numerator and denominator. And it came into use in Europe in the 1500s. Let me please ask that when you write your fractions that you do write the bar completely horizontal, and let me show you why. I've had problems sometimes when someone wants to write the number 1.5 and they write it like this, and that looks pretty good and clear. But at some point, the number 1 and the other number 1 start to look a lot more like they're the same size, and I start wondering if that's 1.5 or 11 halves. I don't have near as much trouble when you're writing it like this because it's completely in front of the fraction bar. So let's go with a fraction bar that's actually horizontal to try to eliminate some of that misconception maybe that might happen just in hurrying through an assignment. So, all right. Did everybody get that one okay? Are we good? All right, models. There are 3 models for fractions that we're going to see used. The first one is an area model, and the idea of an area model is that you can use it to shade in a portion of some kind of a shaped area. And that's really kind of what you saw on those first 3 diagrams with the rectangles and the circle, is that you've got some kind of an object that has space inside of it divided in some equal way. So you might have, and I'm going to use the fraction on all these diagrams. I'm going to use the fraction 3/4 to do this. So you have some rectangle, and it's split into 4. Hang on just a sec. And then 3 of the 4 shaded in. So, area model. The second one, this is the one I have not shown yet on any of my pictures, is the number line model. And this is a partitioned number line. So you have a portion of a line, and you've got sort of like the 0 and the 1, if you will, marked. And then you've partitioned the number line into pieces that are equal in length. So the first one here that I've got is 1/4. This would be 2/4 or 1/2. And then this would be 3/4. So the 3/4 would be this particular dot right. There we go, right there. So that's a number line model. Number line models really work well when you're talking about distances of something for some reason, whether it's actually a legit fraction or if it was a bigger number even than like a number like 3/4, when you're talking about 3.7 or something like that. Number lines really work well when you're talking about like miles somebody's run or something like that, or an image of driving somewhere. The set model was the CHIPS model that I showed you before. So that looks something like having sort of concentric, and usually it's circles. It wouldn't necessarily have to be. There are benefits for it being circles, though. I'll explain in a second. So if we had 4 circles and we had 3 of them shaded in, this would be the number 3/4. The benefit, the drawback, let me say, of this kind of a model is you can't automatically say, well, I have 4 chips and then I'm going to give 3 of them to you. What if I have 5 chips? Well, if I have 5 chips and I want to give you 3/4 of them, that's a problem, right? That doesn't work out well. And I can't really divide up if you're thinking about something that's actually like a poker chip or like money. I can't really just take a pair of scissors and cut that into pieces and make sense of that. So there are some limitations with a set model that the area model doesn't have. I mean, I can take an area model and split it into whatever size and shape that I want. There's no problem with subdividing those kinds of things, but I can't really subdivide actual objects very well. So this set model does have that limitation. All right, so you probably have seen, well, I know you've seen this before, but you may not have ever heard it called the fundamental law of fractions, but it is the fundamental law of fractions. The fundamental law of fractions says that if you have a fraction a over b, and you have another number n, and it's a non-zero integer. So it actually works whether it's an integer or not, but we're only working with integers, which is why it's defined this way. Non-zero What this is saying is that I can multiply by that value on the top and the bottom of a fraction, and it doesn't change the value of the fraction. Right? So like over here when I drew my model, I actually wrote in 2 over 4 in the middle of that number line diagram. But likewise, I could have written 1 over 2, right? It would be the same thing. 1 over 2 is just the same number, but multiplied by 2 on top and bottom. Okay, you can get 2 over 4. So that's all the fundamental law of fractions is saying. And what you're usually using it for is in the other direction. Usually, you guys start with something that looks like this with numbers in there. On the right-hand side, the a times n over b times n. And you do something to reduce it into the a over b. That's the direction in which we usually use this fundamental law. But it can be used the other direction as well. Simplest form is doing that very same thing. It's reducing something so that we can get rid of any of those factors they have in common. So a rational number a over b is in simplest form when the denominator is positive. And this notation is actually used in chapter 5 in our book, but if you haven't actually taken the other class, you might not have seen it. That says the greatest common divisor of the numbers is 1. It's just a fancy way of saying you can't divide both numbers by the same thing unless it's by the number 1. So maybe you have the number 3 and the number 7. Well, 3 and 7 don't divide by anything evenly except the number 1. So that's what it means to have a greatest common divisor, is you'll be able to reduce it. And then that is the a and b have no common factors greater than 1. They have no factors in common other than 1. All right, so what we're going to do is we're going to actually try an example where we're going to create some equal fractions. So we've got the fraction 7 over negative 14, and our job is to write down 3 fractions that are equal to 7 over negative 14. So I want you to take about 30 seconds and write down three fractions, and then we'll see what kind of things you guys came up with. There's tons and tons and tons of answers, right? Infinity of answers. All right, somebody give me one number that you wrote down. 1 over negative 2. Okay, another one that's not that one. 6 over negative 12. And what did you have?
14 over negative 38.
Negative what?
38.
38. 28 maybe? Yeah, I think 28 maybe.
Yeah.
It's okay. We'll fix it. Okay. These are all great. There's something else that you could do that you probably didn't think about. You could also do this. The negative on top or the bottom doesn't really matter. It's the same thing. Basically, it's just multiplying by negative 1 on both of them, right? So you can also switch where the negative is. So there's lots of things we can write down. Some of you, in fact, I think all of you who gave me these examples noticed you could, at least the first two, noticed you could reduce them and then do something with a reduced fraction. That's helpful. If you reduce it to the 1 over the 2, then you can come up with all kinds of things really quickly. But you can also take the 7 over the 14 and do something directly with that to multiply that by like a 2 over 2, which was what the 14 over the negative 28 was. So lots of ways to get equivalent fractions using the fundamental law of fractions and simplest form. All right, so here's a little bit of a different one. What about this is a little awkward?
Powers.
There's powers involved, right? You can't cancel powers. It doesn't work. And I can give you a real quick example of why it doesn't work. So let's just do a number example of why it doesn't work. Let's say you had 1 over 2, and you have 1 squared over 2 squared. Well, 1 squared over 2 squared is 1 over 4, but if you could cancel powers, that would be 1 over 2. And that doesn't work, right? So canceling powers is not a legitimate operation that you can do. So that's kind of out. So what might we try instead?
Make into simplest form. Well, opposite.
So like what? What would your first step be? Can you give me an example?
So you do 42 squared, I guess.
Okay, so do you actually want to multiply 42 times 42? I don't.
Try to reduce the fraction and leave the power.
That's also something to think about, and in some sort of sense, Andrew, it works, but we run into a problem as well. So let me kind of take a couple of the things you guys have said and do something slightly different. Instead of actually multiplying the 42 times 42, I'm just going to write them down. Okay? So that's my concession at the moment of what I'm willing to do. Okay, so that at least eliminates my sort of weird and awkwardness about looking at the squares. Yes?
Do you prefer that we do the times like multiplication with the dot instead of x?
Please don't use the x because we're going to use them for variables very soon. I don't know if it's in this lesson or the next couple of ones, but we are going to be using x for variables. So yeah, don't use the x for variables for what we're doing. I know that sort of depends on the age that you teach and what you're teaching. But when you hit some of the stuff about fractions, it starts to be problematic some of the time. So we're going to stick with that one for now. Yeah. Thanks for asking. Okay, so we're back to 42 and 35s everywhere. What do you want to do?
What if you broke it down into their factors?
We could do that. What would you like to break 42 into? 7 and 6? That sounds like a good plan. And I would have two of them, right? 7 and 6 and 7 and 6. What then about the 35?
7 and 5.
Okay, now what? Yeah, now we can actually divide out the 7s, right? 7 divided by 7 is 1. 7 divided by 7 is 1. So we're reducing based on that fundamental law of fractions. Can I do anything with the 6s and the 5s? I can't. 6 and 5 have nothing in common besides number 1, right? No common factors but 1. So the last thing I'm actually going to be able to do is what? Yeah, multiply back out. So this would be 36 and 25. I don't need to factor the 36 and the 25 because they already were factored and we didn't have anything in common, so they still don't have anything in common. So this really is my final answer. I actually did this one on purpose as well. Is there anything that bothers anyone about this particular answer?
Well, not about the answer. I just have a question.
Yeah.
How come you can't like multiply just like switch around like the 6 and the? Oh wait, actually no, right.
Okay.
Yeah.
Did you answer it yourself?
Yeah.
Okay, that's great. This
The numerator is bigger than
numerator's bigger than
the denominator.
the denominator. For some people that really bothers you, I can tell, yeah.
6 squared and 5 squared.
Yeah, you could write it that way. It would be reasonable to write this. You could leave an answer written in that form. We're about to, I think it's in Sex 3. We'll talk more about exponents and such. And so sometimes leaving it in that form is a reasonable way to leave it as well. But for some of you, this whole idea of the numerator being bigger than the denominator is a problem. Like it does not feel good. Here's kind of the deal on this. If the original problem starts out top heavy, which it did, right? Then it's perfectly fine for the denominator, for the answer to also be top heavy, for it to be an improper form. If the original number starts out as a mixed number, then the answer needs to be in a mixed number. So it's the context in which we encounter the numbers that we're dealing with that tells us what the answer should look like as well. So on this one, it's okay that the 36 over the 25 is how it's left because it started out with 42 over 35 squared, each of those squared. Okay, any questions on this one? A little bit awkward, a little bit different. All right. We're going to do some equality of fractions, I think is what it looks like next. All right, so two fractions, a over b and c over d, are considered equal if and only if AD equals BC. So sometimes I have very creative, artistic people who like to think of this in another way. And I get this image, and I'm told that this is a butterfly. So that's a great visual imagery, especially for your kids who are visual learners, who really see the image of it, of what's going on. That's very nice. The phrase that you've probably heard associated with this is what? Cross multiply. So if you in fact have something equal, then you're able to cross multiply. And they're in their state equal. If the a times d equals the b times c, it also means those fractions were equal to start with, so we can use this in either direction. We're going to take a look at an example where we're comparing a couple of fractions. These fractions are 3 over negative 12 and negative 36 over 144. And we're trying to decide if they are equal. There's at least 4 ways to do this. One of them is the way that we just looked at on the last theorem, which would be to cross multiply, right? So we'll call that option number 1. So option number 1 is to cross multiply. And in particular, if the numbers are small, cross multiplying is very nice. That said, these numbers are not small. And the negative on the second value, the negative 36 over 144, we just have to decide where we want the negative to be. I'm just going to put it on top for no particular reason, okay? So if we cross multiply, and if you have a calculator with you, go ahead and grab it for the sake of time here. I need to know what is, we'll do 3 times 144 first. What is 3 times 144? 432. And then what is 12 times 36? 432. And it's positive as well because we had a negative times a negative, right? So this one checks out. 432 equals 432. So the fractions are equal, right? Now pause for a moment and think about what would happen if you didn't have your calculator. Yes, because would you really want to multiply them? Probably not. You might not be too bothered by the 3 times 144 because it's a single digit times something, but the 36 times, was it 12? It's not going to be a super quick and dirty kind of thing to do. I mean, it's going to take you just a little time. So, Kayla, what was your suggestion?
Reduce negative 36 over 144.
Excellent. So one option then is that we could reduce the fractions. So, and we will reduce both of them simply because we have values that we can do that with. Let's start with our 3 over negative 12, just because it's easier. What will 3 over negative 12 reduce to? Right, because what did you actually do in order to get that to happen? Yeah, we can divide the top and the bottom by 3, which is the same as multiplying by 1/3, by the way. So this is actually 1 over negative 4. The values on the other one are a little bit harder to maybe work with just because they're bigger. I have negative 36 over 144. I'm going to guess just at face value looking at this that you don't say, I know for sure and certain that 144 can be divided by 36. 12. I wouldn't, but I would know they could both be divided by 12. So times tables of 12s are often taught to children all the way through your 12s. So looking at that and saying those are multiples of 12 is probably a reasonable place to start. And then I end up with the negative 3 over the 12, which I then would recognize that that's the same as the negative 3 over 12 I had before. If you didn't recognize it or if you were dealing with some other kind of fraction that didn't readily just jump out at you, you could do it one more time. Then, of course, you would get the negative 1/4. And these two things are equal. So the fractions that we started with originally also are equal. So reducing the fractions is a second option, often helpful. What would a third option be? I bet you guys have thought of something before that might work here. How about we would get a common denominator? Now the easiest way to get a common denominator is not going to be very completely simple and clean on this one. I'm just going to show you how it works with numbers that are, you would never do this in this problem, let me say that. But there are problems for which you could do this that would work really well. So let's say that we wanted a common denominator for these two. And what was my other one? 36 or 144. The easiest way to get a common denominator under any circumstances in terms of not having to think about what should the denominator be is to simply multiply the two denominators together. It will always give you a common denominator. Perhaps not the most nice, neat, and tidy one, but it will give you one. So I would multiply this one by 144 over 144. and I would multiply this one by 12 over 12. So again, for the sake of time and the fact that you guys have your calculators with you, we're going to do this with a calculator. If you were working with numbers for which you would actually do this process, they wouldn't be this big, and you wouldn't have to use a calculator. But what is, somebody grab one for me, what is 3 times 144? What is it? 432. Oh, we were into that one before, didn't we? What is 144 times 12?
1,728.
Awesome. And the other one's going to be the same thing, right? We've done the problem already twice. So if we do multiply the numbers out, we are in fact going to get the same 432 on top of 1728. I mean, again, we just compare at the end. Yes?
Would it be 3 over negative 12?
Oh, yeah, true. It doesn't end up mattering in the sense that the value is the same whether it is, but you're right, that's how the problem started, so we'll put it in the right place. Yeah, thank you. There it is. Okay, good. There's one other way. It's very related to the one that I just did. The one I just did was called common denominator. But you've heard another word used with that before called the least common denominator, or maybe a least common multiple, which is along the same idea. So the least common denominator. Now, what a least common denominator does is the same thing as before. It finds a common denominator. It just finds the smallest one instead of getting 1,728. So you're comparing the 12 and the 144, and hopefully you're recognizing that I can take the 12 and I can make it a 144 easily, right? So what would I have to do to take my 12 and turn it into 144? You multiply this one by 12. So sometimes common denominators are just, you look at it and you just see them. Sometimes they're not, but this one's not too bad. So this is 36 over 144. And we can compare these here and see. Now, to be honest, I think in this particular one, reducing or least common denominator are the easier of the two to do because the numbers are just nice for doing that. But all four of them work, and they will give you the right answer. So this is kind of a cool one. Okay, a couple more things before we quit for today. Along the same idea on checking to see if numbers are the same, we can also check to see which number is bigger. So if they don't equal each other, they're not equal to each other, we can still do this idea of cross-multiplying, but when we cross-multiply, we end up with one of them bigger than the other one, then we know that the fractions were bigger than the other one. So, for instance, you see that same A over B and that same C over D, and if you draw that same butterfly, you still get the AD and the BC. But if you see that when you multiplied, the first number was bigger than the second one, that means that the first fraction was bigger than the second one. And that's it. That's how you can decide. And again, you can do that in multiple ways. We're going to do one more example before we head out, and then call it quits for today. So here are our three numbers, 13 over 20, 3 over 5, and 7 over 10. On this particular one, we could do the cross-multiplying and see which number is bigger than which number, but it becomes trickier because there's three of them, which means I have to do two at a time, and it's not very clean and neat to try this process with three numbers. But thinking back to our ways of comparing if the numbers were equal over here, it might be nice to do one of the other methods, either reducing or finding common denominators instead of cross-multiplying. And these ones lend themselves to something in here in particular. Least common denominator works really well here. So let's take a look at what we have. Here's 13 over 20. I have 3 over 5. And I have 7 over 10. So thinking about the denominators of 20, 5, and 10, what's the least common denominator among those? 20, which means that the first fraction doesn't need any work at all. We're just going to leave him alone. The second one does, though. What are we going to do with the second fraction, 3 over 5? Right, and now I want you to be real careful. We're multiplying it by 4 over 4, right? So be careful not to say multiply by 4, because we want both the top and the bottom both multiplied by 4. So that's 12 over 20. How about the 7 over 10? Right. Multiply by 2 over 2. So that gives me, 14 over 20. All right, so which one is the smallest?
3 over 5 is.
Oops, sorry. What did you guys say? 3 over the 5? 3 over 5. Which one's next? 13 over 20. And last? 7 over 10. Now, I am saying that first, second, last because it says ascending order. Ascending means it goes up, like when you ascend the stairs. You could likewise be asked for something in descending order, and you'd want the biggest one first. So when you're listing these in order, we want to list the fractions we were given. We don't want to list the ones with common denominators because that's not how the problem started. We want to answer the problem the way it started. So 3/5, you can put less than 13 over 20 is less than 7 over 10. You could also just put commas between them because of the way the question's actually worded. We know that your answer is going in ascending order if you've done it correctly, and that will be okay too. All right, so we will pick up next time with a couple more examples of these and finish up this section then.